Professor, we managed to sort out all technical problems, hopefully, and we have Guillaume Allais in line, and he's going to give a talk on scoped and type staging by evaluation. Go ahead, Guillaume.
Okay, hi. Sorry, everyone, I couldn't be down in London with you, but the teaching term started yesterday. Yeah, so this started as an attempt to understand Anna Škovač's work on two-level type theory and how to use it to do stage compilation. So this was, I'm hearing some echo, so let me stop this. Okay. Right, and to do this, what I did is that I opened Agda and I started doing my favorite thing, which is to formalize languages in a scoped and typed way, and then trying to see how the staging and the two-level go up. So the goal here is to have a language in which we can do generic or metaprogramming in a way that is we are able to use at least the same language, maybe even a richer language. It should be type safe. I don't want to have type errors at code generation time. And it should be with no abstraction cost whatsoever, which is a usual problem when we use like a universe of descriptions, for instance, to do our generic programming in. So let's start with a quick example. So here I'm defining the diagonal of a circuit. First, we have this gadget. Let's just ignore all of the indices, but what the type of DOP is saying is that we have a term of circuit type with one input and two outputs. And you can see the circuit on the right-hand side here. It's implemented using a mix combinator, but it doesn't really matter for this talk. And then we have this function here called diag, which will take a circuit that has two inputs and one output and return a circuit with one input and one output. Again, there's a lot of noise with quotes and splices and so on, but we can just ignore them for now. And the idea of this combinator is that we grab the circuit that's passed as an input, and then we form the circuit that first takes the one input, duplicates it, and feeds it to the gate. And this is implemented on the left-hand side using a lambda, and then quotes and splices and sequential composition and so on. And then finally, we can use this diagonal function to describe the NOT gate as the diagonal of the more fundamental NAND gate. So this mentions a lot of like function application, lambda abstractions, the Brown variables, etc., even though the language of circuit doesn't have these kind of facilities. So luckily for us, the staging will get rid of all of the higher order aspects of the language, and then we'll end up with a proper circuit. So not at the bottom right here, we can see that it will partially evaluate to what we expect, the sequential composition of duplication and the use of the NAND gates. So then let's see how we can implement this in Agda. So I'll try to give a quick refresher of scoped and typed syntax and semantics, and then how we can patch it to have a minimal two-level type theory. So let's start with simple types. For the simply typed lambda calculus, we have a base type, alpha, and then we have a type of functions from A to B, which are also two types. So in this presentation, and generally I find it easier to never mention the ambient scope, go back to Martin Love style inference rules, where we assume there's an ambient gamma, we never talk about it, we only talk about the adjustments we're doing to it. So on the left-hand side here, you can see we're threading gamma everywhere, but on the right-hand side, we have equivalent rules where we're only mentioning in the bottom right that we extend the current gamma with a fresh variable of type A when we go under a binder. So to do this sort of stuff, we have a bunch of combinators I'm not going to introduce. You can read about them in the paper, but I will show them. I will show you how we can write these types now. So you can ignore the for all and the fat arrow, etc. These are the combinators that are doing all of the threadings. But morally, what you see is that on the left-hand side, we have a constructor whose type is, if I have a variable of type A, then I can build a term of type A, and on the right-hand side, you would have the corresponding inference rules. So if we have an application, it's a similar process. If we have a function, well, a term for a function of type A to B, and a term for an argument of type A, then we can get a term for a value of type B. And on the right-hand side, you have the corresponding inference rule. And finally, the last piece of the puzzle to get the simply type lambda calculus is lambda abstraction. And here there's a bit of noise again from the encoding, but you can see that apart from the noise, the rules look a lot the same again. So on the left, you have the constructor for lambda abstraction. If I can build a term of type B in an environment extended with an A, this is the same as being able to build a term of type A arrow B. And so when we put all of this together, we have this really compact definition of what it means to have a well-typed and well-scoped language. And then we can write our first example. It's a very boring one, I'm sorry, but it's just the identity function from A to A. And here we just use a lambda abstraction and then use the variable immediately. So this is in the Brown syntax. I didn't give the definition of var, but you get the feeling it's just going to be 0 and successor, basically. So once we have this, one thing we're typically interested in is defining a normalization function for it. And a really nice way to do this is to go via model construction, an intuitionistic model construction. So the first key ingredient in building such a model to get one of, right, so we build this model so that we can write this evaluation function. So this evaluation function tells us that if we have an environment assigning to every variable in gamma a value in delta, then provided that we have a term in with variables ranging in gamma, we can produce a value with variables ranging in delta. Right. So the first key ingredient in designing such a notion of value, in building such a model, is to have Kripke function spaces. So for this, again, we have some really nice syntax that encapsulates the idea of Kripke function spaces. So here you can see it's defined as the box of a function space between two predicates of a context. The box is inspired by modal logic, and it's telling you that something is true in every possible extension of the current context. So a Kripke function space between P and Q is something that will, in any possible extension of the ambient context, give you a function from P to Q in that world, basically. And then ignoring, again, the noise from the syntax, etc., the important thing to see is that on the right-hand side here, we have this double lambda thing, which is a way to say that we have a semantic notion of lambda that allows us to build Kripke function spaces. And then the next definition gives us the double dollar, which is like a semantic notion of application, stating that if we have a Kripke function space, then we can actually use it in the current world and actually get a proper function space in the current world. So once we have this, we can build the model by induction on the types that we're interested in. The value of type, the base type, will just be a term at that type. In principle, we could enforce that this is a normal form, but in this talk in particular, we're not really interested in about normalization, just about evaluation. So I'll stick with just term. And then the value of type A to B is interpreted as a Kripke function space from values of type A to values of type B. So this is a standard model construction, intuitionistic model construction for the simply type lambda calculus. Then I mentioned earlier environment, telling you there were mappings from variables to values. This is what this record definition is saying. And then the important thing to know about environment, apart from the fact that we can look up the value associated to a variable, is that we can extend an environment. And this is we have this very generic type of extend saying that if you have an environment for variables in gamma at the current ambient type, then in any in the current ambient context, then in any extension of the context, if you get a value in that extension, then you can build an environment for variables in gamma extended with A living in that extended context too. So what this is saying is that basically we can always embed the current environment into a larger context and also throw in extra values. Once we have all of these elements, we can build the evaluation function. And it is now purely structural because we've introduced the right notions. So you can see that a variable gets interpreted as a lookup in the environment. A syntactic application becomes a semantic application where the subterms have been evaluated recursively. And then a syntactic lambda becomes a semantic lambda where we recursively evaluate the body in the current environment extended with the value that was just given to us by the semantic lambda. So this is the standard definition of this modern model construction. And now what we want to do is extend the language with two-level features and also get a new model construction that will accommodate this extra expressivity. So let's look at a minimal intrinsically typed two-level type theory. So the idea behind this two-level type theory is to be able to clearly state what should be present at the static level and will be evaluated away during compilation, during staging, and what is purely dynamic and will stay behind. So here we have a silly program that applies the identity, but a dynamic identity to an argument which is built using a static identity applied to the dynamic identity. And then what we want to have after staging is that all of the static parts go away and we end up with just an application of the dynamic identity to the dynamic identity. So to make all of this formal, we need to say what the different stages are. You can ignore the phase argument here. It's a purely technical matter that's discussed in the paper so that we can have a precise notion of normal forms. But so here we define two stages. We have the static stage, which will go away during staging, and we have the dynamic stage, which will be the code that remains after we've partially evaluated our programs. And then we have our notion of types. So our base type is available both in the static stage and the dynamic stage. And then one thing that Andras remarked is that our function types need to be homogeneous in the stage they live in. So this is what really makes it work. And it's enforced here by saying that they can be at any stage, but it needs to be the same stage that's used for the domain, the codomain, and also the overall type of the functions. And then we have this strange gadget of quoted types. So you can think of it as code. So it takes a dynamic type and it gives you a static type corresponding to the programs that are going to eventually evaluate to a program with the dynamic type that's associated to it. Once we have our stages and types, we can give the definition of our language, again, in intrinsically typed and well-scoped way. So this time we can once again ignore the phase annotation and mostly the stage two, except for the last two cases. So first we start with the same constructors as for the simply typed lambda calculus. We have the variable, we have application of a function to its argument to get a value, and then we have lambda abstraction. All of these, because we are building a minimal two-level type theory where we have the same features available in the static and the dynamic phase, are fully polymorphic about the stage they can live in. But then we have two new constructs. We have quote, which turns a dynamic term of type A into a static term of type code of A. This is the trivial notion of a program that will eventually produce a dynamic term of type A. It's basically just embedding one that's already there. And then we have splice, which allows us to take one of these codes for dynamic program of type A and turn it into an actual dynamic program of type A. And so that's where some computation will happen during staging. And this is all we need to have a very minimal two-level type theory with staging. So now that we have the syntax, we need to also extend the semantics so that we can actually residualize these programs to get purely dynamic programs. So our goal is once again to write an evaluation function that will, provided an environment and a static and a term, return a value. So this time our notion of value, because it is indexed by the stage, will be defined by case analysis on the stage. So the value for static terms will be defined by an auxiliary definition called static, but the value for dynamic terms will be purely syntactic terms, because we want to partially evaluate away all of the static parts and end up with proper terms for the dynamic parts. And then you have the static definition below, where the static terms of type base type are just the empty type. That's because we don't have any constructors for our base type. If you had, say, the natural numbers, then you would have a bit more structure here. You would have actual natural numbers as the static values. The static values of type code for an A is actually a dynamic value of type A, which is to say just a term of type A. And finally, the static functions from A to B are the Kripke function spaces from static values of A to static values of B. And we can once again define the evaluation function. It's purely structural. Let's just ignore the few first cases for var, app, and lam for now. We can focus on the quote and the splice, and you can see that in the model, they're just the identity. Their meaning is just the identity. And then this is what is really interesting, is the meaning of app, of application, will depend on the stage. So application in the static stage, remember that these static values are actually computing, so the functions are become Kripke function spaces, and so we use the semantic application for Kripke function spaces here. But the application for dynamic terms, because they're purely syntactic, will become the purely syntactic app constructor from the term family. And it's the same for lambdas. The static lambdas become Kripke lambdas, semantic lambdas, and then the dynamic lambdas are purely syntactic objects. We don't really care about the arguments passed to B here. So the take-home message is that the model construction for the staging of this two-level type theory is a mix of the normalization by evaluation model construction we use for the standard STLC for the static parts of the language, and then for the dynamic part of the language, this is basically the usual definition of substitution. This is the action that we see in substitution. So this gives us a minimal two-level type theory, but of course what we'd like to do in practice is have something with a bit more features. So one throwaway comment in Andreas's paper is that the meta language can actually have a lot more features than the object language that we end up with after staging. And so in the paper, I have an example of a radically different meta and object language, where the meta language is this fully fledged functional language that I showed earlier, and then the object language is purely circuits. And so here you have an example of the sort of things you can do this way. It's maybe a bit scary, but you have the diagram below describing what it does. It takes a function from a Boolean to a very simple circuit with one output and one input, and turns it into a circuit with two inputs and one output. And the second input is basically a control signal telling you whether the function should be applied to true or false. And so this is effectively a generic tabulating gadget that will turn any function into a circuit. And it's defined purely in these things. Okay, so what next? Well, one interesting thing we could do is try to prove the soundness and completeness of the staging using a logical relation. I expect this is just deploying standard techniques. We could have a dependent type circuit description language. So the problem with the tabulation function I showed you earlier is that it's for circuits with a set number of inputs and a set number of outputs. But of course, we maybe like to have a generic definition of tabulation instead. It would be nice when we want to have the exact same language at both levels to just get a description of the standard functional language and then automatically lift it to a two-level construction. Everything is very, has the same structure, so it should be possible to write this generically. And finally, I showed you that quote and splice had a very boring meaning in the model. They were both the identity. And it would be nicer to have computationally interesting quotes and splice. So I've already found two, which are, again, dealing with circuits and functions from bit vectors. But it might be interesting, maybe some of you have ideas in mind of cases where you could actually have interesting quotes and splices that would actually have a computational content. Thank you.
Thank you, Guillaume. We have time for a few quick questions.
Hi, Guillaume. This is Sam Lindley. Thanks for a very nice talk. This is very pretty. Had you considered extending this to multiple stages?
No, I haven't, but this is a feature in Android's original paper where basically you can have an index, you can have an infinite tower of stages, and then every partial evaluation stage will lower the whole language by one step. So I imagine this would be doable. Yeah.
And with heterogeneous languages, so different languages at each stage, do you think that would work?
Right. I mean, the construction is fairly generic in the usage of the stages so you have a single family, but because of the indexing, you can ensure that some constructs are only available at certain stages. So you could definitely do this with more than two also.
Thanks.
Do you have any other questions?
Just one comment, but I think you have a first stage in which you deal with the semantics, the crypt function spaces, and the second, which is syntactic. So I think your approach is more applicable to the two-level cases, because otherwise you have to have a lot of semantics levels. Do you agree?
Well, so I think that you would basically define in parallel potentially semantics for each one of the layers, and every time just shaving off the top one while staying purely syntactic in all the ones below.
Okay, then thank you again.